Okay, this is the Lincoln Inn Fields Cafe, which is a linear building which has a single story on the roof, and I'm not really drawing it to scale, but what we notice about the building is it has this set of posts that run along it, and the ground is sort of below the building, and it's on some form of little pads. And the reason for that is firstly because the ground is a bit sloping, and secondly because the building's made entirely of timber. So if we look at a plan of the building, we see this isn't really drawn to scale, but sort of roughly showing the proportions in principle of how the structure works, and we're talking about the structure. And then what we notice is there's lots of frames of the structure that run along the building, and then sort of subframes of what are called they're called mullions, sort of window posts. And in that structural frame, it looks in section. There's sort of two sections to think about. So one is the frame of the building, and it has a beam that goes across quite low, and those beams are supported on timber posts that on either side. And then it has this sort of strange arrangement where there are posts above. There's posts in the midspan which supports this beam here, and because it's near the ridge of the roof, it's called a ridge beam. And there's quite a thick roof build up over it. I'm sort of drawing this from memory. I went there again this afternoon to have a look, and we have the floor, and again that floor is somehow suspended over the ground, and if you look underneath it you can see what look like concrete pedestals. So the cafe is in here, and you sit in here and have a coffee, but there's fundamentally quite a simple structural frame, which are these beams that go across. And when we look at those, we can see that they're painted timber, but they're absolutely full of cracks. And some parts of the building are actually not glazed, so some parts of the building have a solid wall. I think the bits on this side where the loos are and the kitchen are less glazed, and here where there's views of the park and the tennis courts are this way. I'm just drawing these to indicate this is the entrance, and there's another entrance there. So sort of drawing a door and door swings. And there's some end walls. And actually in the end wall, there's actually a window on the edge, especially on this elevation. So this is solid. I'll draw that as solid with the window. And then when you're in the space, and we're finding a long elevation, so a long section. So we see this is cutting a section through here. That's an indication of a section line. Hope it fits on the video. This being the end wall of the building. The floor down here, and the ground underneath. I'm not going to draw the rest of it because it'll clash with that one. But what we have is quite a deep ridge beam, and then posts that sit on these cross beams, and then every other post has a sort of diagonal brace, and all this stuff is notched together. And if you look at it in detail, you'll see, with a thinner pen, you'll see that this thing, all these beams are cracked, and actually some of these are cracked, and there's lots of cracks in the timber. And the reason it's cracked is because the whole building, well, the frame of the building, is made from something called green oak, which is basically oak that's been freshly cut down. And because it's freshly cut down, it has lots of moisture in it. And timber, it's quite interesting. If you have your tree, and if you think of your tree trunk, and you have the rings, that there's many more rings in a tree trunk. But what happens if you think about this in detail? These are like lots of fibers, lots of tubes that run up the tree. And in timber, those have the strength. So timber is very different from, say, something like steel, and it's called anisotropic, which means that it has different strength in different directions. So a timber beam is full of these tubes, and that's called the grain of the wood. So timber is much stronger along the grain in the same direction as these tubes. They're made of lignin and something else. And what happens is when the tree is felled, it gradually dries out. So these all shrink, and in shrinking, you actually get cracks because there's less space. So all of these elements shrink, and what tends to happen is you get cracks sort of radially through. So obviously this isn't made of logs; it's made of timber beams. So what we see is those cracks kind of from things shrinking go through the section. So this again is a section through one of these. So those are the cracks. There's nothing really to worry about because the beam still works. It's just it's a symbol that it's a sign that it was originally bigger and it's got smaller, because inside buildings they tend to be dry and warm, so the timber shrinks. The other thing that's quite interesting about the building is the stability. So if you look at these joints, they're all pegged, so there's no sort of bolts, steel bolts, stainless steel. If it was timber, if it was oak, you would always use stainless steel. And you can see that the frame isn't, if you push this sideways with the, say, wind load, this would rack over, the frame would tilt, because these joints aren't stiff enough and strong enough to resist and sort of be rigid and make that a rigid frame. The way the building designers have got around it is in the ceiling you'll see there are stainless steel tie bars, and they effectively make they're different in each bay. Well, they're the same, but they kind of alternate. And again, I've kind of slightly cartoonified this drawing because the building is actually longer and has more bays. But what effectively happens is that this creates a truss. So the edge of the building are what we call the chords of the truss, and these tie bars cross brace the thing in plan, and they transfer any of that wind load, which is sort of, say it's blowing on the side of the building here, they transfer it through the action of the truss. So the structure bends in plan, and it transfers it into these solid walls at the end, which are called shear walls. So they take the shear, and if we drew them on here, I don't know what's inside them, but say it's probably solid timber, or it could be a sort of timber cross brace. But that gives the building its lateral stability. And then each building has to have lateral stability in two directions. So in this direction, it's done by that. In this direction, it's done by these solid walls. on this part of the building. Again, shear walls. So if we look at there, this whole area doesn't have any windows. The bit where the cafe is does. So that's how the lateral stability works, how the building doesn't fall over sideways. And then it's difficult to see under the building because it's got sort of some kind of netting to keep rats and vermin out. So, but there'll be some kind of post, and the foundation, I don't know what the foundation is. There's lots of trees around there, and I expect because it's in the middle of Lincoln Inn Field, it's probably lots of what's called made ground, so lots of ground that's been put there when the houses were built. And the first houses were built around that square in sort of the 1600s. So I imagine there's lots of dead bodies and plague pits and all sorts of things. So I imagine that there'll be piles going through the made ground. I'm sort of drawing one bit of drawing over the other because I've run out of space, but that would be then going into the lower earth, so the more geologically original ground, which would be clay, possibly gravel. So the building, this is sort of how the building works. Quite interesting structure. I mean, what else can I say? You notice on these, you get some sort of stepped joints, and you see sort of pegs in all of the connections. So these are what are called mortise and tenon joints. So if you have say a timber post, that would have a slot cut out of it, maybe all the way through it, and then the member that comes in we call structural beams members sometimes, and that would have a sort of tang, what's called a tenon, which would go into the mortise. So that's sort of a close-up of I've actually drawn it upside down, but how, say, a structure there, how that joint would work. So a timber framed structure made in a very, very traditional way, with green oak, which has shrunk and oddly got stronger. So green oak starts off at a certain strength that's quite strong as it is, and then it's felled, dries out, and gets stronger with age. So things to watch out for: stainless steel connections, lots of cracks. It's interesting looking in the building that quite a lot of there's sort of inserts which aren't part of the structure. They're just pieces of cladding and pieces of enclosure for the kitchen, other things. So the building has a separate and distinct structural frame that is there, and then there's other cladding and internal partitions. So if you go in the loos, for example, that's all completely separate from the structure, and it's built after the structural frame was constructed. The roof is interesting in that you can't really see what's inside because it's all covered in plasterboard on the inside and zinc sheeting on the outside. But I expect there are timber joists and insulation, and there were some roof lights in here as well. So those tend to stick up quite high. So there's some interesting steps in the roof. But again, the structure of the roof is really only spanning from the supporting wall to the central ridge beam. The load path then coming down there, that weight is transferred down this post, makes this beam bend. That beam is supported on these side frames, and then the weight is transferred into these posts and travels down through compression in the column, down into the ground, through these raised pads. So that's a rough idea of the structure. I hope that makes sense, and we'll talk about the next one.